A century after Einstein predicted them, two 4-kilometre laser rulers felt spacetime itself quiver by less than the width of a proton as two black holes collided more than 1 billion light-years away. In 1915, Einstein recast gravity, not a force, but the bending of spacetime. A year later, his equations predicted something stranger, that accelerating masses should send ripples of that curvature racing outward at the speed of light. But the effect was so faint that Einstein himself doubted it could ever be measured. For decades, the only evidence was indirect, a pair of dead stars found by Hulse and Taylor, whose orbit was shrinking at exactly the rate you would expect if it were bleeding away energy as gravitational waves. To catch a wave directly, though, you would have to measure a change in length far smaller than an atomic nucleus across kilometers of steel. So here is the question. Could we actually feel spacetime stretch and squeeze as a wave rolled past? And by feeling it, listen directly to the most violent events in the universe, collisions that give off no light at all? LIGO's answer is a giant letter L. One laser beam is split in two and sent down two 4-kilometre arms set at a right angle, bounced off mirrors hung as ultra-quiet pendulums, then brought back together. And here is the trick. The two returning beams meet in opposition and cancel. With the arms matched, no light reaches the detector at all. Now, let a gravitational wave roll through. It doesn't push the mirrors. It stretches space itself along one arm while squeezing the other. For an instant, the two arms no longer match. The light no longer cancels, and a flicker of brightness appears where there was darkness. A ripple in space-time has become a signal you can read. That is the whole idea. And the wobble is small beyond imagining. The arms change by about 1 part in 10 to the 21st. Over 4 kilometers, that is a shift far smaller than a single proton, a tiny fraction of its width. To measure that, LIGO had to hush every competing tremor, distant earthquakes, the heat in the mirrors, even the quantum jitter of the light itself. But a single detector can be fooled by a passing truck, a far-off quake, a stray footstep. So LIGO was built twice. One detector in Washington state, another 3,000 kilometers away in Louisiana. A real wave from space sweeps across the whole Earth, arriving at both sites within the 10 milliseconds it takes light to cross between them. Local noise does not keep that appointment. On the 14th of September, 2015, both detectors caught the same thing, a rising chirp, a tone sweeping up in pitch and then cutting off. The signal earned its name from that very date, GW150914. It was two black holes, each around 30 times the mass of the Sun, spiraling together and merging, more than 1 billion light-years away. Laid against Einstein's equations, the waveform matched almost perfectly. The discovery was announced in February 2016. A 100-year-old prediction, confirmed, and with it, a new way to see. Telescopes gather light. These detectors listen to the vibration of space-time, catching objects that shine no light at all. 2 years later, LIGO and its partner Virgo felt two neutron stars collide, seen at the same moment in gravitational waves and across the spectrum of light, and watched that collision forge gold. What makes it beautiful is the refusal to accept that a proton-scale measurement across kilometers was simply impossible, and the decades of stubborn craft it took to silence the world enough to build an ear for space-time. 1 century from a prediction to a tremor. and the universe was suddenly full of sound. Beautiful experiments.